Okay, can you hear me? Yeah, thanks. There are more buttons on this headset than I know what to do with. I thought I'd turn myself off. Okay, I want to start by giving a formula for what I generally call the one sum of two graphs. So the k sum of two graphs, where you take two graphs x and y, and you identify k vertices of x with k vertices of y. It's more or less impossible to work with if k is 3 or more, and not easy if k equals 2. If k equals 1, you can work with it and it's useful. So the problem is to work out the characteristic polynomial of this graph. So I'm going to take two graphs x and y and merge a common vertex, which I'm denoting by a, and the new graph is z. So this is a one sum of x and y. Now the key thing is, okay, there are a couple of ways of proving this. I'm going to use a generating function argument. And so what I'm going to think about is, well, first I start thinking about the closed walks that start at A in Z. Now, I can't do much with that, but if I think about the closed walks that return exactly once, they divide themselves into two classes: those that start at A and stay on the left, and those that start at A and stay on the right. So I can say that the generating function, this is the sum rule for the closed walks in Z, start return to A exactly once. It's just a sum of the corresponding terms for x and y. And at that point, we're basically done. We know that from the sequence rule, we can express the closed walks at A in terms of closed walks returning exactly once, and vice versa. And I don't expect you to remember, but this is the formula. So we get what's going on there. Okay. So we just do that, and so now we have generating functions for the closed walks in Z that start at A, the ones in X that start at A, and the ones in Y that start at A. And we have a formula for these in the form of phi of graph drop A over phi of graph. Now there's a problem in that the generating function is I minus TI inverse, and for our purposes, it's often more convenient to work with TI minus A inverse. And so every so often you've got to start putting in T inverses. And it's fairly easy to leave one out, but I've got it right this time. So this is the formula relating the generating function for characteristic walks expressed in T inverse in terms of the characteristic polynomials. So you use that and you get this formula, and then you clear denominators and you finally get this formula. So you get x, y drop A, x drop A and y, and then finally minus T times x drop A, y drop A. So that tells us that the spectrum, the characteristic polynomial of Z, depends on the spectrum of X, the spectrum of Y, and the spectrum of X drop A, and spectrum of Y drop A, and nothing else. So those four things determine. And we'll see how to use this as we go on later on. So my point is that this is an easy consequence of the generating function technology. We're using the sum formula and the sequence formula probably a couple of times, and we get this identity. It can also be proved using a determinant argument, and I think it was first written down by Schwenk. His name will come up again later on. Okay, so we can do this computation. So, I mean, this is useful. You can get a recurrence for the characteristic polynomial of a path, because the path, a path is a one sum of a path of length 2 and a path of length n minus 1. So you can get recurrences and things. So it's quite a useful formula. To use this formula, I want to talk about, and for other reasons, I want to talk about cospectral vertices. These will come up when we start talking about, particularly continuous quantum walks. So they arise then. So I want to talk about, and they're interesting in a number of different ways. So vertices in a graph are cospectral if the vertexes are subgraphs x drop A and x drop B are cospectral. And so, for example, to give a very trivial example, if there's an element G Wilson group that sends A to B, then x drop A is isomorphic to x drop B, and so they're cospectral. In this case, we say that A and B are similar to vertices, which you can send one to the other by an automorphism that's said to be similar. And so similar vertices are necessarily cospectral. Now, a slightly weaker condition is that if X drop A is isomorphic to X drop B, and we say they're pseudo-similar, so the assumption is they're not similar, but the vertices of graphs are isomorphic, we call them pseudo-similar, and these things are still co-spectral, obviously. Okay, now you may think, well, surely there aren't any examples of things like this, and I think I got on the next slide. So this is a construction due to some chemists a long while ago. What we've done is I've taken, and there are lots of variants of this, but it's just a simple case that works for now. So I've taken the 6th cycle and put triangles on every second edge. Now I'm picking out 3 vertices, 0, 2, and 4. And we'll see why. My plan is so I've got this graph now. The first thing is that these 3 vertices are similar. You rotate through 2 pi on 3, and you get the same thing back again. So these 3 vertices are similar. Okay. But now what I'm going to do is I'm going to delete the vertex 0. And so from this graph on 9 vertices, I get a graph on 8 vertices. Okay. Now, and I think I've drawn it wrong on the right. So let me have another attempt. So deleted 0, 6 is adjacent to 1. 1 is adjacent to 2, and 3 is adjacent to 7. Oops. I want that right. Not the renames. That's a 7. 3, and that's 1, 5, 6. Now so we just constructed this new graph by deleting a vertex from that graph. Now the point to notice here is the vertices 2 and 4 are strongly co-spectral. If you delete this, you get a K2 and this guy, a triangle with a tail or length 2 added to it. If I delete 3, I get K2 and a triangle of size 3 with a tail length 2 attached to it. And so the vertices 2 and 4 are pseudo-similar. Now, there are lots of generalizations of this. There's nothing particular about using triangles. The important feature is that to get things that are pseudo-similar is that first, that these guys form an orbit, so they're pairwise similar. And secondly, that the automorphisms which fix 0 fix 2 and 4. Okay, and so those 2 things are all you need to make this work. And so you can take longer cycles and put more decorations on the outside, but this works. And so, and the another thing you can prove that if you have 2 pseudo-similar vertices, Bill Cockay and I proved many years ago that you could always obtain them by this construction. Okay, so pseudo-similar vertices give you co-spectral vertices, and so this is one fairly convincing way of getting some vertices which are co-spectral but not similar. Okay, of course, it's easy enough to run Sage and throw out examples. The next example is a tree, and I was saying more about this in a moment. So this is a tree on 9 vertices, and it was found by Schwenk for reasons I'll explain in a little while. And it's got the 2 vertices 4 and 7 are co-spectral. Now, in this case, when you delete 7, you get a path of length 7 and isolated vertex. When you delete 4, you get a path of length 3 and a path of length 4 with sort of a double tail. So these 2 vertices are not pseudo-similar, but they are co-spectral. Now, how would you work it out? Well, you can use the one-sum formula I gave you earlier to work out the characteristic polynomials of the various graphs that you see there. And so that's roughly what this stuff is doing. So you can compute the characteristic polynomials, and so if you decode what I've written here, so here I'm working out the characteristic polynomial of S with 7 liters. So that's a path of length 7. So you take a path of length 4 and a path of length. The answer is right. So I don't want to go into this. Probably not. It's not going to do it. It's stuff a mess. So now Schwenk found this by just a direct search. This was more or less pre-computer times. It might have been a computer somewhere which would have done it for him, but he told me he was waiting a long line to get tickets to a football game, and he had a stack of cards with trees on them, and he eventually found this graph with these two vertices that are co-spectral. Now, the reason they're interesting, I'll come back to in a minute, is if these two vertices are co-spectral, you can take a graph X, one sum with a graph X, and join it to 4, or take it one sum of graph X and join it to 7, now you get two graphs. Those two graphs are co-spectral. So you can use this to construct co-spectral graphs and to construct co-spectral trees. Now, we're coming back to that. I hope I don't forget. And Schwenk made good use of that, as I'll say. The last on the list is that if I take a strongly regular graph, any two vertices in that are co-spectral. And so I'll just leave it as a claim for the moment. It's probably not an undoable exercise at this point, but it's not worse. We will just leave it at that for the moment. So again, so if I take a Latin square graph, in particular, I pick a big enough Latin square that's some 5 by 5, I can get a Latin square in 6 by 6 where there are no automorphisms. And so I get a graph of 25 or 36 vertices with no automorphisms, and every pair of vertices is co-spectral. So strongly regular graphs give you a large class of examples. Finally, this is a tree that my friend Brendan McKay found many years ago. You'll learn nothing much by looking at it, except it's a tree on 16 vertices if I've drawn it right, which is not entirely a given. And there are two vertices here, 6 and 3, and they're co-spectral. In fact, and the same thing applies here. If I take a one sum of some graph here, or one sum of the same graph there, those two graphs are co-spectral, but their complements are also co-spectral, and the Laplacians of the graphs are co-spectral, are similar, okay? And the so-called unsigned Laplacians are similar, the line graphs are similar, and the distance matrices of these graphs will be similar. So essentially, any polynomial you might think about, you get a pair of the graphs you get not be distinguished by any of the natural polynomials. Now, Schwenk's example will give you graphs that are co-spectral. Okay, and Brendan and I later found a construction which gave us graphs that were co-spectral with co-spectral complements, but this in some sense gives you anything. There's presumably an infinite sequence of graphs like this, but I don't think anybody's ever tried to write them down or find them. Okay, so one of the reasons we're going to see that co-spectrality is a condition for perfect state transfers, so it's going to matter to us as we go into quantum walks. But another reason it's interesting is because there are a lot of different characterizations, which is generally a good sign that the concept you're looking at is what we're thinking about. And so this is the, that should be a, yes. So the comments that A and B are co-spectral, this is the X drop A and X drop B are co-spectral. Well, that's the definition, so there's nothing we need to think about. Now, this is saying that the number of closed walks of length K starting at A is equal to number of closed walks of length K starting at B for all K, non-negative. Now, that tells you that the walk generating functions are equal. And that's, of course, implied by the fact that, in other words, the 5x drop A on 5x is equal to 5x drop B on 5x. So B implies C. I'm leaving this as a kind of an exercise. The thing to notice, of course, is that the spectral idempotents are polynomials in the adjacency matrices. And so from C, we see that all polynomials in A have the AA and BB diagonal entries equal. And so therefore the idempotents have the AA and BB entry equal. I'm going to leave this as an exercise, and you don't have to think about the last one. If two vertices are similar, there's an automorphism that takes one to the other. If they're co-spectral, you get something which is trying very hard to be an automorphism. You're getting a matrix whose square is equal to identity. Okay, it commutes with A, and it swaps A and B. Because the Q squared is equal to identity, it swaps A and B. It sends A to B and sends B back to A. Now, so in a sense, Q is trying quite hard to be a permutation, but it's not. Okay, but there is this Q. And we've used that occasionally, but I'm not sure we really understand what's going on there. Yeah, and so finally I come back to what I was talking about with Schwenk, that if A and B are co-spectral graphs, vertices in X, then so are these two graphs. Okay, now and now we think going back to Schwenk's example, where we could take X to be his tree on 9 vertices and Y to be some other tree, and so you can get infinitely many pairs of co-spectral trees. But what Schwenk did was much stronger. What Schwenk proved is the proportion of trees on n vertices that are determined by the co-spectral polynomial goes to 0 as number of vertices goes to infinity. So the jargon is that almost all trees have a co-spectral mate. Okay, now, so the two parts to it. The Schwenk's argument so the Schwenk proved this in his PhD thesis. The one part of the argument is if you have a tree and on the structure and it contains a copy of Y, then you can move it over there and get a different tree most of the time. Now, that part was never published, and fortunately, it's in his thesis though, but a couple of other people, including Kevin McAvaney, came up with a nice counting argument to prove that part of it. The other part is that you have to prove that the proportion of trees that contain this sort of thing, so that Schwenk's tree attached to one of the roots, the proportion of trees that contain that goes to 1 as the number of vertices goes to infinity. And that's a counting argument, and that's not, we don't teach those things these days. That involves some asymptotic analysis. It's not trivial, but it was standard machinery at the time. So Schwenk proved using this that almost all trees have a co-spectral mate. Now, from McKay's tree, you get not only that co-spectral respect to adjacency matrix, but the co-spectral respect to all these other matrices. So the complements of co-spectral, if you use McKay's lemma here instead of Schwenk's, the complements of co-spectral, line graphs are co-spectral, the adjacency matrices, the Laplacians are co-spectral, and so on. So, I mean, yeah, it's a very nice result, and it's and the proof is there are 2 complicated steps to the proof. Any questions at this point? So so this is some terminology that Brendan McKay and I introduced. We say a graph is walk regular if if all vertices are co-spectral, if A to K has constant diagonal for all K greater than or equal to 0. So a couple of remarks here. If the graph is walk regular, then it's automatically regular because the diagonal of A squared is giving you the balances. The AA entry, I'll just call that the BB entry of A squared is the valency of the vertex B. Okay, so walk regular graphs are regular. If the graph is walk regular, so is X. Now that's a consequence of the first factor. Okay, so you need to know that the graph is regular, and then this is a pretty easy exercise. Vertex transient graphs are walk regular. Well, the vertex lead subgraphs are all isomorphic. Okay, so that's all right. And the other comment about walk regularity is that if X and Y are walk regular, so are their direct product and their Cartesian product. Okay, so you can think of walk regularity as being a kind of a combinatorial relaxation of being vertex transitive. Okay, if a graph is vertex transitive, it's regular. It's vertex transitive, so it's its complement. This doesn't make sense. And the direct and Cartesian products of vertex transitive graphs are vertex transitive. This also works for the other products, the strong product and the lexicographic product, but we're not using those, so I didn't bother writing that down. So anyway, but still, this is just definition. We'll walk regular if A to K has constant diagonal, and this is a kind of relaxation of being vertex transitive. Okay. Now, actually want to need a somewhat more general term. So a graph is, or first thing, if a graph is walk regular, then the spectral idempotents each have constant diagonal, because they're polynomials in A, and A powers of A have constant diagonal. So if a graph is walk regular, the spectral idempotents have constant diagonal, and that's what this says. The shared product with I of E sub R is some constant C sub R times A times I. Now, we actually know what this constant is, because we know the trace of E sub R is the multiplicity, and we know the entries of ER are all, diagonal entries of MR are all equal. So C sub R is the multiplicity of the Rth eigenvalue divided by a number of vertices. Okay, that's not too important right now. My point is we do know what this is. Okay, I was just too lazy to write it out. Now, I want to come up with a generalization. I'm going to say a graph is one walk regular if it's walk regular above. And this, so walk regularity is a condition between a vertex and itself. Now I want a condition on vertices and neighbors. So what this is saying is if I take the shared product of A with ER, then I just get a scalar times A. Now again, we can work out what dr is with more effort, but the idempotent looks like a scalar times the identity plus another scalar times A, and then the rest of the entries are filled out in some fashion that we're not saying anything about. Are there any questions about that? Is that clear? Now, this one walk regularity is can be used as a combinatorial version of arc transitivity. So the graph is arc transitive if any pair of adjacent vertices, any order pair of adjacent vertices U and V, and any second pair of adjacent vertices U to V primed, there's always a graph that takes U to U primed and V to V primed. Okay, and so this is the combinatorial definition of that. Now, you're not really used to arc transitivity at this point, and that may not be a huge help, but in a certain sense, we don't need it. We have this hypothesis. And well, the reason we need it is short. I'm going to prove a theorem assuming some graph is walk regular. And then you might say, well, what are the examples? And then I can turn around and say, well, any arc transitive graph. So the Pearson graphs, for example. Now, the theorem I want to prove, now earlier on, I proved an upper bound on the size of a co-clique in terms of the eigenvalues. Okay, and I called it a ratio bound. There's also an upper bound on the size of a clique. Now, to get my upper bound on the size of a co-clique, I assumed my graph was regular. So it didn't hold for all graphs. Okay, I assumed the graph was regular. Now, to get that upper bound on the size of a clique, I need something stronger. I need the graph to be one walk regular. Now, from my point of view, this is a huge annoyance. I mean, cliques and co-cliques just complement one another. Surely you should be able to get similar results under the same hypotheses. But for some reason, to get information about cliques, you need a stronger hypothesis. And it's not really clear to me why that should be true, but it is. And so in any case, I wanted to derive the bound. The other point about this is we're getting the same ratio that we saw in the co-clique bound. And that's why I think of these as ratio bounds for cliques and co-cliques. There's also this is also a lower bound on the chromatic number, but I won't be proving that till much later in the course. So it's a natural number. Now, I'm not sure who the clique bound is due to. Anyway, well, it's a good point. So I want to prove this theorem. So the first thing I'm doing is I'm working out the diagonal entries of the idempotents, and it's just the argument I gave you before. We know the trace of the idempotent is multiplicity. The entries of the diagonal entries of the idempotent are all equal, and so therefore the diagonal entries are equal to M sub R on N, the number of vertices in the graph. Now, the second thing is we know that A applied to E sub R is equal to theta R times E sub R, because the E sub R is a projection on the eigenspace. And so now what I'm effectively doing is taking the trace of this. Okay, so we take this. Well, it's equal to the trace of A times ER. That's just that again. Now, at this point, we use something which I threatened you with before, but we haven't used since. The trace of A times, well, everything's real. The trace of AB is equal to the sum of the entries of A circle B. So the trace of AR is equal to the sum of the entries of A circle ER. Now, I remind you again, sum is just the sum of the entries, and it's very easy to verify this. And I did make the remark that this is often useful. And this is the first example. We haven't done too many calculations, but this is an example where it's true. Okay, so we replace that. Now, at this point, we realize, oh, but A is one walk regular. And so in particular, we have that this is equal to, when you work it out, the sum of this is the sum of the entries of E sub R corresponding to the edges of A now, or pairs adjacent vertices in A. And now the n times k of those. And so we get this. So we get that theta times m tau is equal to nk, number of vertices, times the valency, times the AB entry. And the assumption here is that A is adjacent to B. And so from that, we get that the AB entry of the R is given by this little mess. Now, the point about that helps us here is we've got this mess here, but we've got this MR on in here, and that's going to play effectively no role. So I'm going to look at the matrix N over M sub R times ER. Its diagonal entries are 1, and the entries corresponding to adjacent pairs of vertices are equal to theta R and K. So what's happening is once I do this scaling trick, if I look at the submatrix of E sub R with rows and columns indexed by my clique, the diagonal entries are 1, and the off-diagonal entries are eigenvalue theta R and K. Okay, so now the next thing we know is that E sub R is posi-semi-definite, and therefore any principal submatrix of E sub R is posi-semi-definite. Okay, and so now we think, oh, but C is a clique. So the rows and columns with the submatrix of the idempotent with rows and columns indexed by the vertices in C has got this form. It's a size of C by a size of C matrix with ones on the diagonal and theta R on K in the off diagonal. Now, somewhere hiding in this is a proof that theta R can't be less than minus K, but I don't really need that. So I'm not going to get into it. Now, since this is posi-semi-definite, the consequence of that, there's a couple of ways I can deal with it, but the simplest one is to say that the row sums are non-negative. Okay, now that's a good sort of training thing to think about, but I'll leave it at that. So that's the saying, because this is posi-semi-definite, the row sums are non-negative. One way of seeing it is that actually, the easy way of seeing it is that the row sum is an eigenvalue of this matrix. The all ones vector is an eigenvector. And since it's posi-semi-definite, the eigenvalue must be non-negative. And so that gives us, I'm going to now assume that theta R is the least eigenvalue tau. And so that the row sum is then equal to 1 plus C minus 1 times tau and K. This is the least eigenvalue. So that's non-negative. So that's where the posi-semi-definite is coming, helping. And then it's just a matter of rearranging the terms and trying to get the signs, the inequalities right when you change signs, but I believe I have this time. So from this, you get a few lines of this, and that's the upper bound I wanted. Okay. So that tells us, as I said, for a one walk regular graph, the size of a clique is bounded by 1 minus K on tau. Now, I didn't think too long and too hard about the examples in this case. I probably should have. It's for the complete graph, Kn, K is n minus 1 and tau is minus 1, and so you get the size of the clique is most n. And so the bound is tied infinitely often. I'll leave it to you to find some more interesting examples. You can show that we haven't worked out the eigenvalues of Latin square graphs. The bound is tight for Latin square graphs. For the Latin square graphs, the entries in each row, the rows and the columns give you cliques of size n. And you can show that that will be that's what this bound gives you. So this is the ratio bound for co-cliques. And I'm not actually sure who has 2-2. And I just want to put in Hoffman proved that the great number is bounded below by the same quantity. Okay, and we'll be seeing that when we come to talk about quantum homomorphisms. Yeah, okay. Again, any questions? Well, in that case, we're going to start on quantum walks. Now, the only source of notes we have for the continuous quantum walks are the notes that Gary, Bill, and I have put together, and they're on my web page for the course. And I guess most of you got them already. So there's a set of notes there, and that they're the only source of notes I know. I mean, apart from the original papers for the topic of continuous quantum walks. For discrete quantum walks, Harmony and I have a book, and there's also a book by Portugal. But I'll be spending most of the time on the continuous walks, simply because it's a bit easier. And we've only got 4.5 weeks, so I'm not, I can't attempt to do everything. We will be considering both continuous and discrete, but as I said, the discrete ones, discrete walks are very useful, but they're also a bit harder to work with. So quantum walks, okay. Now, basically they were introduced as a tool to allow you to copy a state. Now, maybe I can actually say something useful about this. The problem is that in quantum mechanics, there's the so-called no cloning theorem. Whoops. Now, what it basically says is if you have a state given by density D, now if you want to make a copy, well, from the action of quantum mechanics, it says what you're trying to do is you want to give a procedure involving unitary matrices. So a linear operation which maps D to D tends to D. But now if you map D to D tends to D by linear operation, then let's say alpha D would go to, well, alpha squared D tends to D. So this is cloning. Well, you'd like it to be. Okay, but it doesn't work because it's not linear. Now, I suspect this even has a name attached to it, but I mean, it's in a sense nothing more than the fact that the map takes a density D to D tensor itself is not a linear map. So there's no quantum operation which will take this input and give you this as output. Okay. So, I mean, if you're trying to run it, now if you're building up a quantum computer and in the course of computations, you often want to copy states, and you'd like to be able to arrange the copy states. And the observation is that if you deal with a quantum walk, now in this case, you have a collection of states, each of which is a copy of C2. So you have a composite system consisting of copies of C2. So if there are n copies, then it's got dimension 2 to the n, which is something worth remembering. So we'll be operating on eventually on vector spaces of size n, but we're actually sitting inside a bigger space of dimension 2 to the n, and that can be a real problem when you're trying to solve worthwhile tasks, because the matrices you're looking at get pretty big. Now, these things are what we call qubits. Okay, and so you could operate on a qubit, and so you pick a 2x2 density matrix. You can apply a unitary, and you get another 2x2 density matrix. So you can assume you've got your qubit in some state, and what you would like to do is arrange, if you're Alice, is to arrange that Bob over here after you've done your operate, set things up in such a way that Bob ends up with a copy of your state, and you don't have to monitor the process. So basically, Alice sets up her state, starts things, tells Bob to stop at a certain time. When he does, he has a copy. So this is a form of copying. It's a limited form of copying, but it's a form of copying. And that was the reason suggested, and it's a valid reason. Now, of course, it's all a bit hypothetical until people start trying to build full-scale quantum computers. But the argument is that we can use continuous walks to effectively copy a state. Now, there is a cost in a certain sense because you've got to wait a time, so you can't copy instantly. But anyway, that's the no cloning theorem. let's just forget that. Okay. So I want to go. Now there could be other things you do with quantum walks, but that was the first reason that was suggested. So what are the ingredients of a quantum walk? So the first thing is a state space, and for our purposes, well, when I'm talking about continuous walks, it's going to be an n-dimensional complex space, Algebraic space. Okay. The states themselves, I'm going to by and large view as density matrices with trace one. Now, I'm not sure that I've never taken a course in. I did take a course in physics, but I never took a course where anything quantum came up. I think the physicists will normally don't see density matrices until later if they see them, and depending what they do, they may not see them at all, I think. So density matrices aren't the standard tool. They usually work with what I'll be calling pure states, and we'll be explaining as I go on. Okay, and I should make a remark that my view of this issue has changed a bit since those notes were put together, and so I'm more enthusiastic about using density matrices than I used to be. But I'll give you the translations as we go. So we have a state, and a state is state is a quasi-semi-definite matrix with trace one, and it would be an n by n matrix. So it's tied up. So in a certain sense, for us, if we're thinking in terms of density matrices, we don't need to fuss too much about the state space. Okay. Now a measurement. Well, the easy way to explain it is a measurement is given by if you've got the system in a state D, then the results of the measurement are determined by the diagonal entries of D. That's what this is giving us. Now, D is quasi-semi-definite, so its diagonal entries are non-negative, and it's a density, so its trace is one. So this diagonal is non-negative and entry sum to one, so it's assigning a probability to each row or each column of D. Now, in practice, D is going to be indexed by the vertices of a graph, and so you can think of it as assigning a probability to each vertex. And so, in a sense, when you carry out a measurement, the outcome is a vertex. Actually, I'm going to write this down. So the outcome is a vertex. I'll just call it. I can't really use I with probability. And the probability is the A entry of D. Now, I mean, there's a lot of theory going with this, and setting this up experimentally can be highly non-trivial, but we're mathematicians, and so we can just say the result of an outcome of a measurement in this setup is just the diagonal entry of the density. If the density matrix is actually diagonal, then you're doing classical physics and not quantum physics. But so in general, your density matrix won't be diagonal. The other point is that in this setup, I'm working with the setup only used in quantum computing. The so-called jargon is I'm measuring relative to a standard basis. Now, I'll say more about this later, but for the moment, I don't care. This is the measurement. This is what we're doing for measurement. I did say, okay, the jargon was we would have a collection of quasi-semi-definite matrices, summing to the identity, and PI is quasi-semi-definite, and then the probability of observing the Earth. Probability of observing R is the trace of PRD. And this is non-negative because the trace of a product, trace of two quasi-semi-definite matrices is always non-negative, and it sums to one because we assume that these things sum to one. So this is the general version of measurement. The physicists will call this usually, I call it a POVM, or a generalized measurement. Okay, and so in this case, what we're using is that PR is equal to PR transpose. So what we're doing here is a special case of a more general situation. And again, we'll come back to that later on. But for the moment, we're measuring in the standard basis. And so the measurement is just telling us the diagonal entries of the density. So if we want to do calculations, we need to be able to work out what the diagonal entries of the density are at the time we measure. Now, so there's two ways you can change a quantum system. One is to carry out a measurement, and the other is to apply a unitary operation to it. And so any quantum process is going to be a sequence of unitary transformations interlaced with measurement. And the standard setup is to assume you do the unitary stuff first, then you do the measurement at the end. You can move things around actually, but that's the usual assumption is you apply a bunch of unitary operations and then a measurement. Now there's also the so-called measurement-based model of quantum computing, where you actually carry out a series. You create a complicated initial state and then carry out a series of measurements where the choice of measurements determined by the results of the previous ones. Then you get a measurement-based model. So there are a number of models of quantum computation. And so the one that you may have seen, I'll call it, say, the gate model, but there's also this measurement model, and there's the adiabatic model, and the ones using braids. So there are a number of models of quantum computation. The ones that are usually discussed is the one I'm just setting up here. Any questions? So I need to fix up some jargon, because as I said, that physicists will normally be working when they have their introductory course, so speaking quantum computing, they'll be dealing with pure states. Now, a physicist was, if you ask a physicist what is the state of a quantum system, so I've got a vector space, an inner product space, and we're assuming it's 5-dimensional, not what really matters. And the physicist will say it's a unit vector in that vector space. Now, that is wrong. It is at best an equivalence class of unit vectors. So if unit vector Z represents a state, then 1 plus I over root 2 represents the same state. Multiplied by any complex scalar of norm 1, it represents the same state. So the state is really a one-dimensional subspace. Okay. Now, it doesn't, I mean, okay, it's once you're aware of this, there's no problem ignoring the difference, so to speak, but still it's there. And when you're first learning these things, it can get confusing. So the state would really be a one-dimensional subspace. So you're actually dealing with the complex projective space, but physicists don't want to do that, so we don't go into that. So a state is a one-dimensional subspace for them. Now, I've defined a state to be a density matrix. In this setting, the pure states that the physicists work with are the density matrices with rank 1. And a positive semi-definite matrix with rank 1 can always be written in the form ZZ starred. And if its trace is 1, then Z must be a unit vector. Now, the advantage of the density matrices is that it doesn't, if I replace Z by some complex number of norm 1, it doesn't change the projection. So, and this gets even better when you're dealing with 2-dimensional subspaces and 3-dimensional subspaces, so that when you get to that situation, you're more or less forced to use the projections and use density matrices. Okay. The states that we're going to be working with for quite a while will be of this form. So this is just E sub A, the standard basis vector in the standard basis vector in the space of complex functions on the vertices of our graph, and so it maps A to 1, everything else to 0. Now, physicists would say this is an outer product, and write this is something like I'm not sure I'll get it right, but something along these lines. So this would be the bracket notation. Now, if I'm working with density matrices, then there's no way you can bring in the brackets. So you could choose to ignore it. If you're going to talk to the physicists or read the papers, then you need to be aware of this terminology. There are various reasons for not liking it, but we won't go into that. So, as I said, so for a lot of the time, at least initially, this will be our states will be of this form. Okay. Now, the nice thing about these set of vertex states is that they sum to the identity and they're positive semi-definite, so they also form a POVM. So the initial states and the components of our measurement are the same. Now, this is not a requirement, it's just this is what you're working with, and so it doesn't makes your life a little easier in some ways. Okay, but so it might get confusing because, as I said, we're using these matrices in two ways. One is as elements of the initial state, as the initial states, and secondly, they are the elements of the POVM that we're using. Okay. So the transition operators, well, there's two flavors. First is discrete walks, where you have a unitary matrix U, and you can density D goes to U to the K, D, U to the minus K. Okay, and so, well, that's simple enough. And so you're just looking at this sequence of matrices. And so here's your initial density, here's your next density. Clearly, this is a similarity. And so this has got trace one and it's fully semi-definite. So we're mapping density matrices. Now, one problem with this is you can't just use any old unitary matrix. You need to be able to implement it in the real world. Okay? And so that imposes a fairly serious restriction on things you can do. So the problem is you might have a 200 by 200 matrix. And so that gives you, 400,000 entries to fill in. And so you don't really want to work with those. So, so there are restrictions on what you can use for you. And in a certain sense, they're not mathematical. Best you could really say is they can't be too complicated, or they could, they might be sparse, or they might be represented as a product of simple operations. Okay, but we'll come back to that later on. The walks we're going to talk about for a while are going to be continuous walks. And so in this case, they're going to have this form, X by TH, where H is some emission matrix. Now, in fact, it's going to be, most of the time, as it comes to see just below, it's going to be an adjacency matrix of the graph. And so we get this unitary matrix. Okay. Now, because H is, if we're dealing with, well, let's go through the special cases. So there's three special cases I want to talk about. One is H is the adjacency matrix. Second is when H is either the degrees plus the adjacency matrix, which is the sign plus the Laplacian, or the degrees minus adjacency, which is the Laplacian. And the third case will be I times S, where S is a real skew symmetric matrix. Now, putting in the real there just to emphasize, as I said, my default assumption is if I say a matrix is skew symmetric, then you should assume it's real, unless I warn you otherwise. Okay, now in that case, the U of T, when you work it out, is X minus TS. Now, this is a real matrix, this is real. So in that case, U of T is not just unitary, but orthogonal. Now, people sometimes tell you that what makes quantum mechanics strange is because you're dealing with complex things. But I want to assure you, you can get all the strangeness of quantum walks in this situation just using orthogonal real vectors and orthogonal matrices. Anyway, this is the case we're going to be thinking about for quite a while. I have more to say about these later on, perhaps. But so we're going to assume that our emission matrix is actually the real symmetric matrix. One way I think about this is I times our emission matrix is skew emission. Okay, and so the thing you're multiplying T by needs to be skew emission in order to make this unitary. But so you can show fairly quickly this is unitary. It's also symmetric because in this case, because A is symmetric. So that's a freebie. You don't usually expect your unitary matrix to be symmetric, but the matrices we're looking at for quantum walks, continuous quantum walks on graphs, are going to be symmetric. The other point is that the complex conjugate of U is equal to U inverse in no, I don't think I need that. Yeah, no. So and so I generally tend to write things out using inverses rather than complex conjugates, but there it is. And well, the next slide is blank, but I'm used up my time anyway, so I'll stop there. Again, any questions?